Hello, my name is Lauren, and tonight I'm going to show you how I do drift scanning spectrography using my Daub. I've got my 8-inch set up in my backyard tonight, and an ASI 183mm Pro camera is currently set up on it. I've just finished aligning the finder scopes, and now I'm going to go ahead and center up a calibration star as my first step of the night. But before I can do that, I need to connect the camera. So here's how you do that. In SharpCap, you want to go to the upper left where it says Cameras, click on that, and then select your camera. It should be automatically detected. So here's mine. When you select that, it goes ahead and connects, loads it for you. And here's the controls over here on the right. You're going to want to change some things probably the first time that you plug it in. It may have you in an 8-bit color space. It'll say mono 8 here. You don't want that. You want mono 16. And you want to make sure you've got the full capture area. I do. The binning is 1 unless you're seriously oversampled. And your output format, this is pretty important, it should be SIR file. That's going to record like an uncompressed video. It's a pretty big pain to deal with a folder full of PNG frames. Okay, so now we'll come down here to the camera controls. 50 milliseconds is pretty short. I usually start out with 200. The gain at 0 is, I would not recommend using that. You want to always be at least at unity gain. Unity gain for my camera is 111. It will vary. The manufacturer will probably say somewhere what yours is. And down here in the bottom, this took me forever to figure out, is where you can perform a histogram stretch. You have the option of boosting the image using this FX box up here at the top, where you can select like image boost or image boost more. Those are auto stretches. Those can be quite annoying at times, flashing in your face if the scope gets bumped and so the maximum intensity on the screen goes down. So ever since I figured this out, I much prefer set the FX to none, and then this dotted line right here, you can drag around to do your display stretch. So here, if I push it all the way to the left, oh, would you look at that? There's actually a spectrum up there, which we would have no idea if it was at the default stretch. Here's the default stretch. So that's made star hopping so much easier for me. Okay, and my camera is cooled, so I have the cooler set to on, and it's currently cooling to -10 degrees Celsius. I think that's manageable with tonight's temperature. Okay, so to get started, I'm going to go ahead and center up Vega in the finder scope. It's up near the zenith, so I might have to rotate the telescope around, do a meridian flip to get it. Maybe not. Looks like it's close already. Okay. And there we go. There's Vega. Now, you'll probably notice that there's a couple things off with it. It does appear to be somewhat close to focus, but it's going up at this crazy angle. And that's no good for if we want to process this later in spectrography software. We would have to rotate it, and rotating introduces artifacts. So my next step here is going to be to rotate the grating, the diffraction grating, which I'm using to create this spectrum, and I will rotate it on the nose piece of the camera until the spectrum is running horizontally, so I don't have to software rotate it later. So to do so, I'm going to pull the camera out. You see it going out of focus. I'm going to reach over to the nose piece. I currently have a Barlow housing, which is set up so that I can screw the grating onto that and then rotate the Barlow when I want to move the grating, and it allows me more precision. I have a written guide to that on my website and some pictures. Okay, so here I've got it nearly horizontal, but if I can center it up here, it's a little bit difficult to work with the telescope pointed exactly straight up. a lot easier when you look through the finder. Okay, so this spectrum is currently on the left side of the star. See how there's a much fainter spectrum on the right side of the star. We want to swap those places. It's the universal convention in spectrography to have blue on the left side of the spectrum. Well, blue is the side of the spectrum that's closest to the star. I know it's hard to tell with this camera because it's a monochrome camera, but I'm going to rotate it 180 degrees so that that blue goes on the right of the star. And hopefully after that, my camera will be just about ready. Okay, now I've just pulled it out to make an adjustment. I'm sticking it back in slowly. And there's the spectrum. Now I saw down there on the bottom, you can see I haven't quite made it. That spectrum's below where it should be. So I'm applying another rotation. Stick the camera back in. It's getting hard to tell, so I'll go ahead and rotate the telescope to give me some more room. There we go. Okay, now I'm just going to repeat this procedure. Pull the camera out, rotate, stick it back in, see how my adjustment did. Oh, too far. Okay. Easy fix. Just rotate it back a little. Pretty close. Let me make another minute adjustment. There we go. The spectrum is now horizontal. We won't have to rotate it later in software. Now, if you were going for a really precision spectrum, then you may want to get it a little bit closer than that, but for tonight, I don't want to waste y'all's time. So there we go. Now I've put the camera back into the focuser, and I have locked it into the focuser using the set screws, which are on the upper rim of the draw tube. That's pretty important so that it doesn't fall out, and especially with a camera like this, that's a good chunk of change. All right, so now I'm going to pan over until I can see the spectrum well, because the next step is focusing. Now it's already fairly close to focus, but I want to show you anyhow the general procedure. I currently have a 3.8 degree wedge prism on my grating, and that corrects for some of the coma that is a blur that you get inside your spectrum, but it also introduces some astigmatism, which can be another kind of blur if you're not careful. What the astigmatism does is it makes it so that when the spectrum is at best focus, it will actually be taller than you'd think it should be. It looks like it's out of focus, but you have these sharp vertical lines. So I'm going to go ahead and attempt to achieve that focus. I'm just panning the scope around here to get Vega in roughly the position that I want it to be in when I start recording on the sensor, which is in this upper left quadrant of the screen. Now I'm going to zoom in to 100% and come up here. You can see some hints of some lines there, but it's going to be a lot easier to see if we turn the exposure down. Oh, perhaps it was the display stretch that was blowing that out. I'm going to turn the exposure back up, and there's another dotted line way off here on the left. We can move the black point with, and then there we go. And now I'll come back over and yep, there's a spectrum. You can see some Balmer lines, slight darkenings over here, but I'm going to change the focus until those Balmer lines get clearer. Okay. This is a little bit of a race to keep up. The farther north that the star is that you pick to focus on, by the way, the more time you will have to focus, because the star will be moving across the screen slower. Okay, so it looks like this direction is roughly where we achieve best focus. Now, if you're at a high dispersion like I am, the spectrum is very spread out. It turns out that the Balmer lines in Vega and other similar stars are actually naturally wide. So they're not the greatest for focusing because they'll never come down to a small point. So there are some lines from Earth's atmosphere, telluric lines, that are going to be way off on the right side, and I'm going to refine my focus using those. Before I get to that step, though, the very fine focusing, I want to make a point here. See how Vega has now moved into the middle of the screen? It's definitely got some diagonal drift going on here, and I can rotate the camera to eliminate that diagonal drift, and that will make things a bit easier. The spectrum will be holding still horizontally, and it'll also give me a bit of a finer focus. And I can use longer exposures without it blurring. All good things. So I'm going to put my cursor right over the star. Let's watch which angle it drifts away from the cursor. Okay, now I've taken note of that angle, and I can look at the back of the camera and rotate the back of the camera so that what was down here moves by that angle to over here. So the markings on the camera that were on the bottom will move by that angle. There we go, that's roughly that angle. I usually have to make a few adjustments to get it close, but let's see. Now if I put the cursor there. Alright, that is drifting pretty much straight down. So it's going to be easier to find a focus now. So let's put Vega back in the upper left so that we can reach those far red telluric lines. Okay. Now I'll zoom in, maybe 125 this time. Come over here until, aha, see that big dip there? That's a telluric line. Now I'm going to turn up the exposure so that it's more visible. There we go. It looks actually like it's not a telluric line. That looks like hydrogen alpha, so I'm sorry for leading you astray. Let's come over here. I'm going to turn the gain up for working way far out here on the red end. Going to turn it up to about 300. There we go. Okay. Now, where is... Perhaps I was looking at second order. Well, here I'm going to improve the focus slightly. And there we go. Okay, that's definitely a telluric line. Turning the exposure down a little bit. Or perhaps the gain. If you turn the gain down and not the exposure, generally you'll come out with a less noisy image than if you turn down the exposure and not the gain. Okay. Going to recenter Vega. That's pretty much just turning the telescope left now that I have this all lined up. Okay. This focus is pretty close, but I think I can refine it a little bit more. Okay, well this is a good focus for the purposes of demonstration, so I'm going to go with this, and to save this focus, I'm not going to have to refocus throughout the night, luckily. There is a lock screw on the focuser. It's a nylon tipped set screw that goes right in and presses on the draw tube. I'm going to turn that screw, and now the focuser will be prevented from shifting. Even if I take the camera out and put it back in, the focuser is now held in place. So let's make sure. I'm afraid focus was lost a little bit during that operation, which can happen. It's annoying, but it does happen with my focuser. Alright, let's come back over here. Yes, yeah, that's what happened. Alright. Here. So sometimes, if your focuser does have that shift when you put in the lock screw, what you can do is support the draw tube. Try and physically hold it steady as you tighten down the lock screw. In my case, the lock screw somewhat pulled the draw tube inward, so I'm applying a steady outward motion as I tighten the lock screw. And now let's see, is it still in focus? Yes, it's still in focus. Look at that beautiful series of Balmer lines. Beta, gamma, delta, epsilon, zeta, eta, theta, etc. All right. So now we've gone to all this trouble to get focused on Vega. We've set the rotation using Vega. Now we are actually going to record Vega, because Vega has that nifty property of being an A05 star, and we can calibrate all the rest of the spectra that we take tonight using a spectrum of Vega. If you want more precision, like if you're going after science, then you will probably want to take several calibration stars during the night, but to get started, it's fine to take just one. Now, I'm making some fine adjustments to the telescope. I'm trying to get Vega as close to the left edge of the screen as I can. We need to see Vega, the star, in order to align the images when we go to stack them later. But if it's too far in the middle, then we're going to lose the spectrum on the right. And in this case, I'm at a very high spacing, so the spectrum spreads out way to the right. And so if I don't get a calibration spectrum over here, if I had put Vega over here, the spectrum would be running off the edge, and I wouldn't be able to calibrate the red end of any of my other spectra from tonight. Okay, but fortunately I can. So I'm going to name the target. This is pretty important. You name your target up at the top in SharpCap, and then it will put it in a folder with the target name so that you can figure out what's what later. And for settings, I'm going to use unity gain and set the exposure based on the histogram. So I've set the histogram spec to normal. Let's see what 100 millisecond exposure looks like. That's pretty good. I can go slightly higher, and I am going to for reasons that I'll explain in a minute. Okay. Now that the exposure's set, I'm going to line up Vega for a pass, and after that, we can move on to our interesting targets of the night. There we go. All right, Now I'm going to hit quick capture. I've currently got it configured that it'll max out at 1,000 frames if I forget to end it, so it won't fill up my hard drive completely. And I'm just going to let it run. Now, if you were shooting a faint target, then you would want to just let it run until it runs off the edge of the screen. Me personally, I don't know that I want more than 300 frames really. But one consideration if you're going for an accurate instrument response correction is that stars twinkle. We all know that. But when they twinkle, they actually do change color slightly because the atmosphere refracts different colors of light slightly differently. And so the spectra of stars are actually affected by their twinkle on a short time scale. And if you want that to average out, then you're going to want at least 40 seconds or so. And that should average out all the twinkling so that you get an accurate instrument response spectrum. In that case, I would make several passes of Vega until I was sure I had enough frames, but I might actually have enough anyway. I'm tired right now, I can't do the math that well, but I'll just cut it short around, well, I guess when it reaches the end of frame. I was going to do 300 frames, but it's dropping quite a few because these are large images and it takes some time to go over the USB and be read in. Okay, now I'll come up here to stop capture. There we go. Okay, so that came out to almost 300 frames. So next, I have got a plan, because that's a pretty important part to a successful observing session. I've got a plan to go observe the star P Cygni. P Cygni is a, well, actually, I'll just let you see. So I'm going to go ahead and switch over my target name while I'm thinking about it, because I know that the next thing I'll be stopping at is P Cygni. And P Cygni is quite a lot fainter than Vega. Right now, if you notice, everything that's not Vega is looking pretty much black. So if I want to see P Cygni, I've got to increase the exposure, and I'm also going to increase the gain. I find that it's useful to have a gain set to maximum for most targets. And then down here on the histogram stretch, I move the black point, that's the very far left dotted line, over to the center of the peak on the histogram. And then I stretch it as much as I can. Oh look, now we can see there's a few faint stars, faint spectrum. Good, so we're seeing more detail. And in fact, I'm going to turn the exposure even farther up for this star hopping. Let's say 300 milliseconds. There we go. Well, now we can see pretty well. Now I am going to use my finder scope. I'm going to go over to Gamma Cygni. I can see that one easily naked eye. Okay. So here we have Gamma Cygni. And it's not our target of interest, so I'm just using it as a waypoint. I can now see I'm centered on that. And P Cygni right now is above Gamma Cygni. It's along the backbone of Cygnus, this one. So I'm going to move the scope up and over until I can see in my finder scope, yep, there's P Cygni. Now I happen to already know where it is because it's one of my favorite stars, but if you don't already know where a star is, you can use an app like Sky Safari, which has some pretty great star charts, and you can compare the view to your phone. Okay, so now I'm in the vicinity of P Cygni. In the finder, it looks like I'm lined up on P Cygni, pretty much, but I don't see it on the preview screen. And if this happens to you, don't panic. You can do a little sweep. So I'm just going to slide the telescope around a bit. I know what my target looks like. If you don't know what your target looks like, then you should be looking for something like a telltale asterism of stars. For example, oh, that is my target. I guess perhaps I don't know what it looks like all that well because it's overexposed right now. Let me turn down the stretch. And there we go. Okay, but when you're star hopping and you don't know what the spectrum of your target will look like, you can't identify it based on that, then you'll just want to look for patterns. Like, okay, there's going to be one very bright star and it's in this weird box shape with 3 fainter stars, and there's a faint star off the bottom if I want to confirm it. You look for that kind of thing. Alright, so here's P Cygni. It's drifting into view. It's drifting horizontally. That's not what we want. That is causing some blurring of the spectrum. If we zoom in, you'll be able to see. There we go. In fact, the spectrum's looking a little bit out of focus. I guess I should have focused on P Cygni and not on Vega. But it's alright. I can correct that just real quick. You can tell it's out of focus and not simply blurring because of motion, because it's got that circle shape. And that circle shape is what happens when you have an out of focus star in a reflector telescope. Okay, well, to make this easier on myself, I'm going to go ahead and rotate the camera. P Cygni should now be traveling approximately down. I'm going to zoom out so I can find it. Okay, I overshot a little bit. Easy fix. There we go. And I know P Cygni's rising, so I can just push the telescope up a bit in order to get it back into view. Okay. Now I've got it roughly where I want it. I'll go ahead and fix the focus. You notice that the telescope jumps around quite a bit when you touch it, so it's best to let it settle for a second or two when you're testing how good your focus is. There we go. See how that turns into a fine line? And also see how that spectrum is so much taller now that it's in good focus. When it was out of focus, see, it was narrow. That astigmatism flipped from spreading out the spectrum vertically to spreading it out horizontally. So it makes it look like it's a better focus, but then if you go and turn it into a graph, it's going to be all blurry. So here I go. I'm pulling it back into the proper focus. And there we go. Fine lines. Now, I'll lock it with that nylon screw here. Okay, focus shift wasn't too bad. Now I do see that artifact, which I see sometimes, a little bow shape. And still figuring out the cause of that. Okay, so here's P Cygni. Fascinating target. I'm going to fix up the stretch a little bit so you can see it better. See all those emission lines? Those are coming from excited ions in the atmosphere. P Cygni is one of the most massive stars that we know of, so I hear, and quite unstable. It's got a massive amount of that mass is just being blown off the star and its solar wind. That's what we see is the emission lines. It's very rare to be able to see the corona of a star and the solar wind having any effect on its spectrum, because the star itself is so bright it just swamps it completely. For our own sun, we pretty much have to wait until there's a solar eclipse and the whole sun is blocked out by the moon, and then you can see the spectrum of the corona. But here on P Cygni, it's just bright as day right on top of the regular one. Okay, so I'm ready to record my spectrum of P Cygni. I'm going to position it in the upper left. There we go. And the exposure looks pretty good to me. So I'll go ahead, quick capture, and let it roll. Now the same thing applies as with Vega. You want at least 40 seconds to avoid having seeing effects distort your spectrum. So in this case, that should be easy to manage because it's going to drift for at least 40 seconds, and it's not tossing frames like it was with Vega, because 300 milliseconds is plenty long for the image to download. With Vega, when we were at 50 or so, I don't remember exactly what that was, 100? That was too short, and so it had to skip some of the frames. Now, one consideration when it comes to shooting stars, especially up there in the Milky Way area, and especially once you start going fainter. The fainter your target, the more you're going to want to worry about it. There are other stars in the field, and you can't control where the other stars are, and sometimes they might overlap the spectrum you're interested in. Like, see all those faint little buggers there? Now, I'm not too worried because P Cygni itself is so bright, even if a little faint star overlaps it, it's not going to be that much of a difference. Now, you do want to be careful with that if you have intents to use your spectrum for some kind of scientific work. However, if I was trying to get the spectrum of, like, say, this object, well, that spectrum's way fainter, and so I'd need to worry about if one of these faint stars wound up behind it. Let's stop the capture. There we go. It's a good idea to stop it before it runs off the frame because it's less painful. You don't have to manually discard all of the frames where the spectrum was missing later on. Okay, so if you do wind up with a background star behind your spectrum of interest and it's an issue, then don't panic. There's totally something you can do. Same thing you can do, and you should do before each target, is rotate the camera so that the star drifts straight down. Well, when you do that, the relative locations of the stars in the field change. So here I am gently rotating the camera. See how they're moving? Their spectra are always staying to the right of them. So in this way, see if I rotate it up like this, then we've got a star which is overlapping the spectrum down here. That's a problem. Well, if that's the case, all you have to do is give it a slight little twist, and there you go. You've got some separation between the star and the spectrum, and when you record your spectrum, it won't be contaminated. That can get pretty difficult in crowded fields to miss all of the different stars, but it's possible. Okay, so now I have set up focus. I've recorded a calibration spectrum, and I have recorded my target spectrum, P Cygni. I'm going to make a different video which shows processing up those two spectra and showing how you create the instrument response curve and then apply it. But this, now you're done. You can repeat that procedure ad nauseum however much you want and get as many spectra as you want, and then you're just going to be limited by how much time it takes for you to process them up later.